and this will explore localization in 5G and beyond, enablers, methodologies, and challenges, which will cover some of the main technological enablers for 5G and beyond 5G localization, and propose an algorithmic framework for localization and mapping, and also highlight a variety of challenges in designing future radio localization systems. Sharing more about all of this from Sweden, our next speaker is a professor in communication systems with the Department of Electrical Engineering at Chalmers University of Technology. His awards include an ERC starting grant and a Chalmers Supervision Award. He also leads the CrossNet team at Chalmers. Ladies and gentlemen, please welcome Professor Henk Wermisch.
Thank you and good evening. So let me first try to share my screen. Can you confirm the screen looks okay and that the audio is working?
Looks perfect.
Thank you. Good, so first of all, let me thank you for inviting me to present here on this work on localization. I've been working on radio localization for now 15 years, and in the beginning it was a very small and niche area, but now with the introduction of 5G and 6G it's becoming more prominent. Before I go on to the technical part, I just want to briefly mention where I am from. So this here on the right is a picture of Sweden. On the left side is the star. This is Gothenburg, which is Sweden's second largest city and the home of Volvo. Chalmers is a private technical university founded in the early 1800s, and I am part of the Communication Systems Group, which has 9 professors in the area of physical air communication, ranging from fiber optical communication to wireless to hardware limited systems and AI. Good. Now, to get started, I like to pose the work that we do in the form of a challenge. So this is what I call now the 5G Beyond Positioning Challenge. And incidentally, this picture is from downtown Singapore. And of course, when you drive with a taxi in downtown Singapore and you look at the GPS, you notice that the GPS doesn't work. And this is basically because the GPS signals are blocked by all the tall buildings around. And then this immediately leads to a need for a more advanced positioning system that can work in these dense urban scenarios, as well as in indoor environments such as parking garages. Okay, and the way that we phrase this problem is as follows. So suppose that you have a base station on the rooftop of a building equipped with a multi-antenna system. You have a user equipment in the vehicle, also with multiple antennas. And then we want to send a downlink signal from the base station to the user. And this is typically the kind of positioning signal that are sent in 5G today and 4G as well, but then from several base stations. But now we only have a single base station. Of course, this signal goes over the complex multipath environment. And then the question that we ask is the following. From the signal from a single base station in downlink, in an unknown propagation environment, can we localize the user? Can we synchronize the user to the base station? And can we also say something about the orientation of the user, for instance, the driving direction? And you could argue that this is already a quite tough challenge. But we will make it even harder. We also want to provide radar-like mapping capabilities. So we want the user to map the environment to figure out where the buildings are and where the other moving objects are. Next, we want to even do this when the line of sight is blocked. And this can happen when there's no line of sight because of an obstacle. And then still we want to localize the user. This becomes formidably hard. And finally, we want to use these intelligent surfaces, which was incidentally also discussed at the end of the previous talk, as a way to shape the propagation environment and support positioning and radar capabilities, not just communication. And I hope by the end of this presentation you are convinced that all of these are indeed possible. So this will be the outline of my talk. I will start with first a brief basics on the idea of radio-based positioning, and then move on to the concepts within 5G and beyond 5G positioning that are being explored right now. Then I move on with a little bit more mathematical flavor into how 5G positioning really works. So going back to this downtown Singapore scenario, how does it really work? And then based on the available time, I will also go on to talk about beyond 5G positioning with intelligent services before wrapping up with conclusions. Okay, but let's start at the beginning. So the main idea of all radio-based positioning systems is that the radio waveform tells you something about geometry. And this is a picture here that I take from my wireless class at Chalmers, where there's a source on the left side of this building, there's a destination on the right, and a wideband signal is sent from the source to the destination, going over this environment. And if the signal has sufficient bandwidth, this is what the receiver will see. So it will receive as a function of time or delay the received signals. And you see that the signal is very much resolved in delay because of the large bandwidth. And the first arriving path could be from the direct line of sight, and then the other paths could come from the multipath components that arrive later. Important is that each of these multipath components tells you something about geometry. The question is, of course, how to exploit that information. Now, in practice, a receiver will not have access to this very wideband information, but have other kind of measurements such as signal strength, time-based measurements such as time of arrival or time difference of arrival, and angle measurements such as angle of arrival and angle of departure. And I will go through most of these later. Once you have these measurements in place, you can then fuse them or combine them to determine a position. And in positioning, there are two important criteria. The first one is resolution, and the second one is accuracy. And I want to spend a minute on this because they are often confused. So resolution refers to the ability to distinguish multipath in some domain. For instance, in the picture above, you see that two multipath components can be resolved if they are sufficiently far in delay. If they cannot be resolved, they will be blurred together and you have no hope of estimating the delays of the individual paths. So resolution is an important limitation in positioning systems. The second one is accuracy. Accuracy refers to the ability to estimate a single path that is resolved. And accuracy depends mainly on the signal-to-noise ratio. This means that if you only have a single path in your environment, the accuracy can be arbitrarily good just by increasing the SNR. However, the resolution cannot be improved by increasing the SNR. All right, so with these ideas in mind, now positioning is a kind of classical statistical estimation problem, right? You have observations, you have a likelihood function, which describes a statistical model, and you want to infer the hidden variables, the positions. So this means that we can rely on all the tools from statistical estimation theory. For instance, performance bound, using Fisher information theory, a wide variety of algorithms ranging from geometric algorithms, maximum likelihood algorithms, convex optimization methods, and also ideas from Kalman filtering and particle filtering and so forth. We also can use, for instance, the bounds for signal optimization to optimize, for instance, where should base stations be, how should the measurements be designed. And of course, we need to deal with several practical aspects. The most important among those is probably synchronization. As you know, for instance, in GPS, a GPS receiver doesn't just position itself, it also synchronizes itself to the GPS constellation. And without this ability to synchronize, time-based measurements become basically useless. And because the synchronization requirements are so tough, we are also immediately faced by severe hardware limitations. And this will be a theme that I think will occur more and more in 6G. Nevertheless, the field of radio-based positioning is a kind of very safe research field in the sense that whenever people in communication come up with a new technology, we can reuse this for positioning. And this has happened, of course, for instance, for the idea of turbo coding in the 90s, massive MIMO a decade ago, and now, of course, for instance, the intelligent surfaces and artificial intelligence methods coming up now. Good, so this is a bit of background on radio-based positioning. How does radio-based positioning work now in your cell phones? So how it works now is through something called time difference of arrival, where in uplink, as you can see in this picture here, a user would broadcast a signal to several base stations. These base stations are perfectly synchronized and connected to a fusion center. The signal estimated at one base station would provide it with a time of arrival estimate. So the time of arrival estimate at base station I would be the distance between the user and base station I over the speed of light, plus the clock bias of the user plus noise. And so this clock bias refers to the lack of synchronization between the user and the base stations. And this bias is dependent on the specific user, not on the base stations, because as I said, the base stations are all mutually synchronized. From these time-based measurements, you can compute differential measurements. So you take one base station as the reference and compute these difference measurements, and there now the bias is gone. So these different measurements are basically differences of distances. And differences of distances can be geometrically captured by a hyperbola. And this is what's shown on the figure on the right. So there are three base stations here. One of them I call the reference, and then I can compute 2-time difference of arrival measurements, and each of these gives rise to a hyperbola. And then the user is on the intersection of those hyperbola. Now these hyperbola are a bit blurred because of the limited resolution, and this is due to the limited bandwidth of this system. Okay, so you cannot accurately localize yourself. You have some error of maybe 50 to 100 meters in this case. The nice thing is that it is really scalable. You need very few transmissions per device, but you're limited by the base station placement and of course the bandwidth, which is an effect of the multipath non-resolvability. This is what's happening now. So what is the vision towards 5G and 6G? So this is a picture I took from this paper from a few years ago. And there they predicted that future location methods within 5G would provide very accurate localization, so down to below 1 meter for indoor and urban outdoor scenarios, complementing existing radio-based technologies. And there's a lot of radio-based positioning technologies. For instance, GNSS, so GPS, GLONASS, Galileo. They can operate really well, providing high accuracy, but only when there's sufficient line of sight. So it only works in kind of nice outdoor scenarios. We also see 2G, 3G, and 4G, as well as wireless LAN technologies. And each of these are somehow limited because of their resolution, so they have accuracies above 1 meter. Now, again, this was a paper from a few years ago. Now 5G is really here, and we didn't actually realize this 1 meter vision. So if you look at what's really possible, it is something between 1 and 10 meter, not 1 meter. So then one of the authors of this paper actually revised this figure. So this is now the updated vision. So 5G is now shifted to the right, so it can provide accuracies down to 1 meter, but not better than that. And now we replace 5G with 6G, and the hope is now that 6G can provide this very accurate positioning, even in very tough indoor environments. Now, a reasonable question is, why would this be possible? What are the technological enablers to get these amazing accuracies? This is what I will talk about now. So what are the selling points for 5G and beyond 5G positioning? So of course, 5G positioning has been studied for a number of years. And I think a kind of nice paper from a European cost action is this one here. And there it is highlighted that there's a number of properties in 5G that are conducive for positioning. They include high carrier frequency, so the shift from sub-6 gigahertz to about 24, 26 gigahertz. The use of larger bandwidth, so up to 400 megahertz in 5G. A large number of antennas, and here large could be maybe 16 or 20 at definitely the base station side, but maybe also the user side. Device-to-device communication and network densification. So this was the vision for 5G a few years ago. Now, when we look at 6G, things are a little bit different. So the first 5 enablers are more or less the same, high carrier frequencies, but now instead of just going to 24, 26 gigahertz, we will also go up to and above 100 gigahertz. We'll have large bandwidth, so much more than 400 megahertz, maybe 1 to 10 gigahertz of bandwidth. Now, because we go to these high carrier frequencies, we need to counter this with large antenna arrays. We'll have hundreds of antennas, probably at both the transmitter and the receiver side. We will keep device-to-device communication for relative positioning. We will also need network densification because otherwise the links will be too short. But what is new in 6G is the technologies of meta-surfaces, which will allow us to shape the environment, and the use of AI and machine learning to solve some of the harder problems. Now, a question that is kind of commonly asked here is, based on this, will 6G just be 5G plus? So will it be 5G but just a bit more challenging? I think there's a variety of answers to this. I think from my point of view, the most important difference will be when we go to this 100 gigahertz carriers and above, is that we will be much more hardware limited, which means that we from the communication or the positioning fields will need to talk to the circuits people to really understand what is happening and how to mitigate the impairments, and in some cases even to exploit the impairments. And this of course has implications to the waveform. So it is doubtful that 6G will be able to use OFDM, for instance, for the reasons of amplifier backoff. Another interesting thing is when we go to these very high carrier frequencies, the wavelength will become much shorter, antennas will become much smaller, but of course from a localization perspective, objects remain the same size. Objects don't move faster, objects don't shrink. So this has a scalability implication. For instance, when we use smaller antennas with more fine beams, we need to send many more beams in a wide variety of directions to map an environment. And this then incurs more delay. So these are some of the challenges that I see that will be different in 6G than in 5G. Nevertheless, I will spend now one slide each on each of these technological enablers and to clarify why they would help positioning. The first one is the use of high carrier frequencies. So what I show here is also kind of textbook example of a transmitter, a receiver. Let's say both transmitter and receiver have multiple antennas and they operate in a multipath environment. So there's a channel matrix in between the transmitter and the receiver. And if you imagine the transmitter and receiver each has 10 antennas, this is a 10 by 10 matrix, right? So with 100 degrees of freedom in principle. And if you open any textbook from the last few years, they would say to the students, in order to generate this matrix, you would just populate it with IID, complex Gaussian numbers, because that's what represents Rayleigh fading. And this is all fine and well at lower frequencies, but does not fit very well at higher carrier frequencies above 28 gigahertz. In that case, channel models tend to become more geometric. And this is because there is no shadowing anymore and the propagation effects are different. So when you open a millimeter wave paper at these frequencies, you will see a channel model that looks like this. So the channel is the superposition of a small number of paths or clusters. So L would be maybe 3 to 5. Each of the paths would be characterized by a complex channel gain, alpha L, a delay, tau L, so that's the propagation delay of that path. And then you have these A vectors, these are the response vector at the transmitter and the receiver. And they depend on transmit angle, so this theta TXL is the angle of departure at the base station, in this case the transmitter, in the frame of reference of the base station. And theta RXL is the angle of arrival at the user side in the frame of reference of the user. And when you look at this, of course, you see that all of these parameters, except for the channel gain, are geometric. So these are very relevant for positioning, because now you have more measurements that you can get from your observations, which tells you more about geometry, so good for positioning. All right, so high carrier frequencies are good because they provide a sparse communications channel, highly resolved in terms of multipath, related to the physical environment. Secondly, large bandwidths. Large bandwidths are good because they allow you to resolve multipath in the delay domain. So this means when two paths are arriving at very similar delays, with a low bandwidth, they are blurred together. But when the bandwidth increases, they become more and more resolvable. And this is what's shown, for instance, here on the right. This is a picture I took from this paper from almost a decade ago now, where they did measurements using 2 gigahertz of bandwidth, where the transmitter was fixed and the receiver was moving. And what you see here in each of the rows is the impulse response as a function of the delay tau in different positions. So as the receiver is moving, you see that this is first path would be the line of sight path. Okay, before the line of sight path, there is no power, but you see here the kind of resolved line of sight path. But you see other kind of patterns emerging here, and these correspond to resolved multipath components. So each of these trajectories corresponds to some object in the environment. Of course, the object is not moving, only the user is moving, but the geometry keeps changing because of the user mobility. In any case, large bandwidth gives you a high degree of resolvability of multipath in the delay domain. And this is also the property that is used in automotive radar, for instance, to get very good performance. In addition to having large bandwidth, we will also have a large number of antennas. And again, in 5G, this will be maybe on the order of 16 or 20. 6G could be on the order of 100 or more. When you have a large number of receive antennas, you get more angle of arrival resolvability. And this is what is shown here on the picture on the right. So I show the angle of arrival on the x-axis. The y-axis is, you can imagine, as a kind of likelihood function. When I have very few antennas, even in the presence of two paths, as shown in this figure, I get the blue curve. So I see basically only one path because the two paths are blurred together. When I use more antennas, the two paths become resolvable. So a large number of antennas at the receiver is very good because it provides you angle of arrival resolvability. Similarly, but not precisely the same, when you have a large number of transmit antennas, you can send narrower beams, and this in principle gives you better angle of departure resolvability. An angle of departure resolvability is very important because it allows you to localize the user, for instance, with angles only. So for instance, if I have a base station here on the left, a user on the right, the base station has many antennas, the user has only one, then the user can estimate the angle of departure from the base station to the user, so it knows it's on a line from the base station towards itself. So this provides lots of geometric information. In any case, large arrays are very good because they provide angle resolvability, which will then be complemented by delay resolvability, as mentioned before. Next, we have device-to-device communication through side links. Now, side links is a somewhat controversial topic, but let's assume that side links will be there. These then provide measurements between devices. So this means that I could provide angle and delay measurements between devices, which then would in turn enable cooperative position technologies, but also radar-like mapping capabilities. So even if neither of those two devices are connected to the infrastructure, by sending these 5G or 6G waveforms, they could determine their relative position and cooperatively map the environment. Next is network densification. So we'll have many access nodes, so base stations or transmitting reference points, which means that we'll have a high chance of line-of-sight connectivity. And of course, you can already intuitively imagine that the line-of-sight link is the most important one for positioning. The non-line-of-sight paths are useful, but they are not the most useful ones. So we really like to have line-of-sight links between the transmitters and the receivers. And well, basically, in order to allow communication, this would be generally available. When they are not available, then we need to look at alternative technologies such as intelligent surfaces. This brings me to my next point. So there's been a lot of talk right now about reconfigurable intelligent surfaces. These are comprised of a plurality of very small elements with controllable phases. This could be controlled in different ways. They are passive, so they don't introduce noise, and they could operate in different ways. So when a wave is coming towards the surface can be reconfigured to reflect back the wave in a non-natural direction. And the direction that it's reflected can be controlled. An intelligent surface could also operate as a lens, so that the wave would go through and it could be focused in a certain direction. Now, this has been used a lot in communication. So for instance, here is an example with a source to destination and an intelligent surface. And now this intelligent surface could provide a controllable high SNR link towards the user, even when the line of sight is blocked. And this has been studied a lot in communication, but from a point of view of positioning, these are also very interesting because they provide new positioning references. If you know where they are, typically they will not move around. So you have to know where they are, what their orientation is. You can use them as reference points for positioning. You can control their SNR, and you can also get a variety of measurements from them, including delay and angle measurements. I will talk more about that later. And then finally, the seventh selling point of 5G and beyond 5G is the use of AI. Okay. So there are problems where the relation between the observation of the channel and the location is really hard to figure out because there is no good model. And in that case, you could, for instance, train a neural network with labeled data. So you provided a bunch of channels, maybe converted to some embedded domain as shown in the picture here, with as supervised labels the user location. And then a neural network could learn the mapping from the channel to the user location. And this can provide also very good performance within this environment. Now, in general, I think AI has amazing potential, but my vision has always been to use it to solve those problems for which we don't have good models. If there is a good model and there's a well-known technique that can solve it, we should use it because that provides explainability, provides ways to do optimal design and so forth. But for those problems that are very challenging, for instance, when we have hardware impairments or the concatenation of multiple nonlinear and stochastic blocks, that's where AI, in my view, really shines. Good, so now we go back to the outline. So I hope now that you've convinced that 5G and beyond 5G have a lot of attractive properties for positioning. Let's go back to our downtown Singapore scenario and look in a little bit more detail what's really happening. All right, so the figure on the right shows a more abstract vision of the downtown Singapore scenario. There's the base station here shown in blue. There's a user, which is the car. The user has an unknown position, shown here as X, and an unknown orientation, shown as alpha, and is also not synchronized to the base station. Right, so the base station sends a downlink signal, and then the signal reaches the user via the line of sight path, shown in blue. And there could be also several multipath components. So the first multipath component can be going through this small object, S1, to reach the user. Okay, so I show this here as a small object like a lamp post, and this object is determined by a position. So it has a 3D position, which I don't know. There could also be large objects in the environments like a wall. So this is what's shown here. And then the signal goes from the base station, bounces off the wall, and reaches the user. And the point where the signal bounces is denoted here by XS. Now, a problem here is when the user is moving on the road, this incidence point, XS, will also move. So this is happening, for instance, when you drive by a skyscraper, and you see the sun reflected. As you drive, you see the sun moving. So this is not maybe the most useful way to describe a building. So if we want to map the environment, we need to have a state definition of all the objects in the environment. And for this, what is usually done is that a large surface is described, the state is described by a so-called virtual anchor. So this is XVA. And XVA is a reflection of the base station with respect to the wall. So it's behind the wall here, and this is a fixed point. So this means when the user is driving, the incidence point on the wall will move, but the virtual anchor, which kind of goes the points from virtual anchor to incidence point to the user, this virtual anchor location will be a fixed point. So this means that the virtual anchor is a nice and compact representation of a large surface. So you already see that the scenario becomes a bit complicated. There's the user, which is unknown, the state is unknown. There are objects in the environment which have an unknown state, so we could have small objects and large objects, and we don't know anything about where they are. So this is really the problem. So we want to estimate the user position, clock bias, and heading in an environment with a transmitter, which has a known position, and then reflectors and objects, scatter points, and we also want to reconstruct the map. So we want to figure out the state of S1 and XVA, if possible. The way that we do this, we start from our standard millimeter wave received signal. So this is this Y of t. This depends on some pilot signal, X of t. So there are dedicated positioning reference signals that are sent. They could be pre-coded with a matrix F, because maybe the signal resides in a low-dimensional domain, and then F brings us to the antenna domain. Then it goes over the channel, and the channel, as before, is described by a few multipath components, each with a channel matrix depending on a channel gain. The receiver response factor with angle of arrival theta L, the transmitter response factor with angle of departure phi L. And then at the receiver, there could be a combining operation, bringing again back from a high-dimensional antenna space to a low-dimensional space. And this is what the receiver has, this Y of t. And now it needs to figure out where are all the objects in the environment. Now, the observations that the receiver can extract from this, we will denote by ZL. So if you have a parametric channel estimator, that can estimate ZL, which comprises for each path the delay, angle of arrival, and angle of departure plus noise. And there are standard channel estimators for this. I will talk about this in a second. And now, there's actually a very easy mapping if I know everything in the environment. So if I know where the user is, so the state of the user, if I know where all the objects in the map are, then I could compute all of those delays and angles. So that's the kind of forward model. The challenge is, of course, that I need to invert this relationship. So I'm only given angles and delays. I need to invert to figure out the user state and the map. And that's really the hard problem here. There's an additional challenge and an opportunity. The challenge is that from the observation Y, we could compute these measurements Z. And these are tuples in this case of 3 dimension. But we do not know which of these tuples corresponds to the line of sight path, which of these tuples corresponds to a previously seen object in the environment, which of them corresponds to a new object, or which of them just corresponds to a noise peak, so clutter. So that's a challenge. So there's a so-called data association problem. On the other hand, there's an opportunity, which is that for each object in the environment, there are 3 unknowns, right? There's a X, Y, Z of that object. But if I have a 3D environment, I have 5 measurements, because I have the time of arrival measurements. And then I could have angle of arrival and azimuth and elevation at the user side, and angle of departure and azimuth and elevation at the base station side. So this means that with enough objects in the environment, I have way more measurements than unknowns. So then in principle, I could have a chance to solve the problem. It also means that when there's no multipath in the environment and I only have line of sight, in that case, I cannot solve the localization problem. Right? I do not have enough information to determine where the user is. So this really shows that in this case, we use the multipath to our advantage. Of course, when there's no multipath, then maybe you wouldn't use these technologies. Good. Now, still the problem is quite complicated, so we break it down into smaller sub-problems. So this is how I would say the flow working between communication and positioning. So most of the time you have communication because you don't need to position yourself every microsecond, maybe every 10 or 20 milliseconds is enough. Every now and again you will send a positioning reference signal or a sounding reference signal downlink to the user. The user then would observe this observation Y of t. It would then do channel estimation to estimate angles and delays. It would then do a data association to match which angles and delays correspond to previously seen objects. And then I would run a positioning and mapping routine to update its own state and map. And then, of course, there will be mobility, and you have these two loops operating concurrently. I will just spend one slide on each of these just to show what are some of the interesting problems that could occur. So the first one is in terms of the signal design. So in positioning, right now the base station is using a so-called positioning reference signal. This is basically a signal that spans the whole frequency band to have enough bandwidth and is orthogonal among different base stations. But there is no real spatial signal design. So a meaningful question is then, how should the base station signals be designed to have the best possible angle estimation? Okay, and this question is a little bit ambiguous because you could have angle of arrival and angle of departure estimation. And then you could solve these problems through a convex optimization approach. So let's look just at some of these. So the figure on the right shows what is the best signal that the base station should send for the user to estimate its angle of arrival as good as possible. In this case, both the base station and the user have multiple antennas, otherwise the problem is not meaningful. And this problem is also only meaningful when you have some side information of where the user is. So we assume this user is inside of this yellow sector, otherwise there's no meaningful signal design that you can do. And what it turns out to be the optimal solution is that you should send a sequence of beams which provide a kind of uniform coverage in this, yellow area around 90 degrees. And what this means in turn is that you should kind of blast as much energy as you can towards the user and as little as possible towards other directions. So the signal design is somehow very intuitive. Things become a bit more involved when you think about angle of departure optimal design. So now you can think of a scenario where the base station has many antennas and the user only has a single antenna. And you want to design a signal at the base station to help the user estimate the angle of departure from the base station to the user. So there is no angle of arrival anymore because the user only has a single antenna. And then when you solve the corresponding optimization problem, you see that the beams you should send look something like this. So they have a lot of emissions outside of the desired band. And this is needed in order to, within the desired band, to have lots of fluctuations. So you see these different beams, they fluctuate a lot in the angle of departure. And these fluctuations really what helps the user to figure out what is the true angle of departure. And then you could, of course, combine both of them to have precoders at the base station that are good for both angle of departure and angle of arrival. And I foresee in 6G, when we want to track individual users, we probably want to design such pilot signals for the positioning individual for each user or for user groups. So I see this as an area that will gain more importance in the future. The second one is channel estimation. So given the observed waveform, how do we estimate the angles and delays for each path while maintaining the per path association? So we want the channel estimator to provide tuples of delays and angles, not just a bunch of angles and a bunch of delays, because then it's hard to figure out which one is associated to which. Now, this is a classical problem already, and the way that this is typically solved is by exploiting the sparsity in the beam space domain and then solving this using compressive sensing. And doing this, of course, provides you much higher accuracy than just figuring out what is the beam direction. So right now in 3GPP standards, what is happening is that the base station sends a number of beams in different directions. The user measures the energy, and the beam with the largest energy, that would be the nominal angle of departure. But that would give a very poor angle estimate, and by using these compressive sensing methods, you can do much better. Now, I don't want to explain in detail how this works because it's somehow classical, but conceptually what you do is you take your observation, which is a high-dimensional object, and then you convert it to a domain where the sparsity becomes clear. This is just what you do when you have a natural image and you apply a discrete cosine transform to convert it to a domain where you see that all the energy is concentrated in just a few of the components. And in this MIMO scenario, this would be called the beam space domain. And in this beam space domain, you can read off the angle of departure and angle of arrival up to a scaling. And you see these different peaks. And each of these peaks now, they correspond to a propagation path. And once you have the location of the peak, you can figure out angle of departure and angle of arrival. Of course, the problem is a bit more complicated because we don't just have a two-dimensional problem. We have a much higher dimensional problem because we have angles of arrival in azimuth and elevation, angles of departure in azimuth and elevation, and delay. So it's a kind of five-dimensional structure that we need to consider. If you want to play around with this, a few years ago I put this GitHub MATLAB code online, which generates a scenario for positioning with objects. It generates a waveform, solves this compressive sensing method, and then positions the user in 3D. Next is SLAM. So now that once we have the measurements, we have the delays and angles, now we need to figure out where is the user and where are the objects in the map. And there are a lot of techniques for SLAM. One of them is the so-called PMBM filter, which stands for Poisson Multi-Bernoulli filter. And the Poisson Multi-Bernoulli filter is very attractive because it's a conjugate prior for many problems. So this is just like the Kalman filter. The Kalman filter, the Gaussian distribution is a conjugate prior for the linear Gaussian model. This means that when you do a prediction and update step in the filter, the posterior distribution is still a Gaussian and can then be used as a prior for the next time step. So this is also what happens here with the PMBM filter, but in a much more complicated scenario. In the PMBM filter, you represent the user state with particles, and then condition on each particle you have a map. And each of these map comprises a so-called multi-Bernoulli distribution, which is, you could see as a bunch of Gaussians, basically. And then in addition, there's a so-called Poisson point process, or PPP, which represents all of the objects in the environment that you haven't measured yet. So they're objects that you think may exist, you don't know where they are, but you haven't received any measurements yet. And then there exists, of course, an update and prediction step for this multi-Bernoulli filter, which is what we use in our tracking routine. So this is what the image on the left will show. So there's a car moving around in an environment. There's a base station in the center. The user is this black circle in the middle. This dome represents the objects around it that it can see. So it kind of captures the field of view. In the beginning, the user only knows where the base station is, and it has some prior of its own location. And you will see it moving around, and as it moves, it will map the environment. So it will try to figure out over time where are the objects. So it needs to figure out the small and large objects. It also has clutter measurements, so it will generate false hypotheses and so forth. Now, the PMBM filter is a quite complex filter. The way that it works is it basically generates all possible associations. So for each measurement you get, it will say, okay, it could have come from this object, from that object, or from a new object or clutter. And each of these hypotheses are weighted with the likelihood function. And you just keep track of all these hypotheses over time, remove the low weight hypothesis, and then you get performance like this. And I think this is among the state-of-the-art filters for tracking. Good, let me go to the next slide. Now, just to give you a little feeling of how this then works in the end. So this is an example from a paper that we did a few years ago. This is a two-dimensional example. So on the left side is a transmitter with location Q and known orientation, known position. On the right is the user with an unknown position and an unknown orientation. So we need to estimate this P and alpha. And then there are some objects in the environment, and we do not know where these objects are. Okay? And now the receiver observes the waveform, will estimate angles and delays, and tries to map the environment. And now I hope you have at least some intuition that this is possible, right? Because for each object in the environment, you have two unknowns, but you get three measurements: the angle of departure, angle of arrival, and the delay. Okay, so you have more geometric information than unknowns. So the way that we solve this problem is we first apply this orthogonal matching pursuit to estimate angles and delays, and then we apply a standard nonlinear least squares to figure out the position. And of course, then you could extend this to other cases with more sophisticated algorithms. And then this is an example of the performance we get. Okay, so on the x-axis is signal-to-noise ratio, y-axis is the RMSE, so how well the estimator is. In red is the performance bound based on Fisher information theory, and in blue is the estimator performance. So we see that we get close to the bound for high SNR, and this is not a very sophisticated estimator. When the line of sight is blocked, what do we get then? Then we get this performance. So we see that we can still localize the user, and you can still operate close to the bound. Okay. And again, even though the line of sight is blocked, because we have enough objects in the environment and enough measurements, we can still solve the problem. And again, we do not know a priori where the objects are, we don't know where the user is, and there's no line of sight. So this is an extremely challenging problem, but still with this kind of relatively simple methodology, we can solve for all the unknowns. All right, so this is the end of my part on 5G positioning. Now I'll move beyond 5G positioning with intelligent surfaces, and that will be the last part of this presentation. So there are different terminologies for these intelligent surfaces. There's LIS, ILS, RIS, IRS, reconfigurable meta surface, and so forth. Some of them mean slightly different things, but I will call them RIS, so RAS, Reconfigurable Intelligent Surfaces, and they will function the following way for a communication application. So this is a figure taken from this paper from 2019. On the left side is a base station, on the right side is a number of users. The line of sight is blocked towards the users. Because if the line of sight was there, probably you want to use only the line of sight and not use the RIS at all. There's a channel from the base station to the RIS. There's a channel from the RIS to each single antenna user. And the RIS itself is characterized by phases. So each of these elements has a controllable phase. And this allows us to write the observation model at each user as follows. So the observation at a certain user is a transmitted signal, the channel matrix from the base station to the RIS, the phase control of the RIS, and the channel from the RIS to the user, plus noise. And now this omega can be changed in such a way to maximize the SNR. And this is basically leading to a high power beam from the RIS to the user without any amplification, so without any noise. Of course, you can extend it when the line of sight is there. And one of the main applications for this is to overcome line of sight blockage and coverage holes. An important challenge in RIS applications is to estimate the channel. So to estimate the channel HBR and HRU is actually really challenging because the RIS cannot estimate anything at all. It doesn't have any RF chains. Now, of course, since RIS has been widely studied for communication, there's now also an interest for localization. And these are figures taken from this paper here. An obvious application would be to do localization when line of sight is blocked, right? Because then the RIS, they provide signals just as a base station would with known position source. A RIS can also be relatively large electromagnetically, and this could lead to near field effect. So we could exploit the wavefront curvature to better localize the users. And there's a number of applications that are considered. So for instance, as localization in very harsh indoor multipath environments, as well as localization in high dimensions, so 6D localization of position orientation using this RIS. Now, what RIS can do, in principle, it can do two things. It can boost performance or enable localization. So boosting performance means that when you have 3 base stations and you put a RIS there, without the RIS you could localize, and with the RIS you can localize better. Similar for radar, so without the RIS you could do radar, but when the RIS is there, the radar performance will get better. So this is boosting performance. What I think is more interesting is to enable performance. So this means that when there is no RIS, you cannot localize. And we will see 2 examples. So one is single base station localization with line of sight, and the other one is single base station localization without line of sight. Now you say, hang on. You had already talked a lot about single base station localization. It is possible anyway. So here we make the scenario a bit more challenging by focusing on single base station localization with a single antenna. Okay. So in this case, the 5G positioning does not apply. All right, so let's look at this case of single base station localization with line of sight. The scenario is shown here on the right. So there's a single base station with a known position, has a single antenna element. There's a user, also has a single antenna element, has an unknown position, and then there's a RIS on the right with a known position and known orientation. This orientation is shown here with a coordinate system. So if there's no RIS, you have no way of localizing the user because the only measurement you get is a delay measurement, and this puts you on an infinite number of balls around or spheres around the base station. So you cannot solve the localization problem. Now, when the RIS is there, you get additional measurements. So the following measurements are available. There's the line of sight delay. Then there's the delay of the path from the RIS. Oh, I'm sorry, I didn't mean to do that. And there's the angle of departure from the RIS to the user. This angle of departure you can estimate by changing the RIS phase profile over time. So this is similar as you would do in angle of departure estimation for analog phased array. Now the time of arrival measurements, you can compute their difference, and that provides a time difference of arrival measurements. And the time difference of arrival measurement leads to a hyperbola. This is shown here in red, and in 3D it would be a hyperboloid. The angle of departure measurement gives you a line. This is shown in green. This will be a line in 2D, but in 3D, of course, it would also be a line. In either 2D and 3D, the intersection of this hyperbola and the line gives you a point. So this allows you to localize the user. Once you've localized the user, you can figure out the clock bias from the line of sight delay. And what I show here on the left is as a function of the position here, the error in localization for for a very simple processing algorithm and including the bound, so we get very close to the bound. Now, so what is important here is that the RIS on the right acts like an additional base station, which is synchronized by the primary base station and has a phased array. So that's basically the functionality that the RIS fulfills in this case. So this is another figure showing the same thing. So this is a top-down view with the base station here on the bottom, the RIS on the left, and I show here the position error bound. So this gives an indication of how well I can localize the user in this environment. And you can see when you're behind the RIS, you cannot localize, of course. And in the environment, you can localize well when you're close to the RIS, because that's when the path loss plays in your favor. It turns out when you're behind the base station, there's this small area where you cannot be localized, and there's some beautiful geometric interpretation for that. Now, nothing is stopping you from putting a plurality of RIS in the environments. You could have 3 RIS, and then you can kind of provide a uniform coverage even with a single transmitting base station. A challenge is, of course, how to estimate parameters from the several RIS, but the way that you can deal with that is by having orthogonal temporal codes for each of the RIS, and then the user can separate the line of sight path or the uncontrolled multipath from the paths from each of the RIS. All right, so now we'll make the problem even a little bit harder. Let's remove the line of sight. So in this case, the user only has the path from the RIS. So the scenarios here shown on the right, there's a base station with a certain location, there's a RIS shown here, and then the user could be anywhere in the deployment environment. If the user has line of sight to the base station and line of sight to the RIS, we now know that they can be localized, as shown before. But if the user is in a shadow of an obstacle, then the line of sight is blocked, then only the RIS is available. So this means the delay measurement you have to throw out, okay, because we can no longer compute time difference of arrival. But what we can do is now exploit the wavefront curvature to localize the user. And now this is shown on the figure on the left. So this is shown the XY coordinate. The red triangle is the base station. The small green star is the RIS. And then the user can be anywhere here. And I'm showing the position error bound in dB meters. So 0 means 1 meter and minus 10 means 1 centimeter. Oh, sorry, means 10 centimeters. Okay. And if we work in far field, so we use a far field model, then the user can be localized again when it is close to the RIS, and otherwise it has some degradation. When we use the near field model, so we exploit the wavefront curvature, then we see that the user can be localized even in the shadow of the obstacle. Of course, there's a severe degradation because we no longer have the very favorable line of sight path, but localization is still possible. So this is something that can provide a kind of location continuity to bridge these gaps when the line of sight temporarily is blocked. So RIS has several benefits for positioning. There's also benefits for radar. And I tried here just to show the most extreme challenging cases with a single antenna base station with and without line of sight availability. So where does this go next? And this will then lead to the end of my talk. So right now, 5G and 4G have mainly focused on communication. When we will use more bandwidth and more antennas, the introduction of AI, the use of radar and sensing within the 5G and 6G system, a more dominant inclusion of localization and an ability to adapt the environment with intelligent surfaces. And this will be leading to one combined 6G system that has all of these ingredients. And I think worldwide this is now appreciated that communication will probably not be possible at very high frequencies without having localization and sensing capabilities built in. There are a number of current EU projects that are investigating this, including the Hexa-X flagship project and the RISE 6G project, so which all try to define what 6G will be. There are many new enablers towards 6G, which leads to many new applications and opportunities. There are also severe challenges, such as the hardware limitations and link budget. If you want to know more, there was a white paper that was published last year, which was led by the 6G flagship and University of Oulu, on the vision of 6G localization and sensing. So let me now conclude. I hope that even if you didn't know, now you realize that radio waves can provide geometric information which is useful for localization. This is what GPS is built on. This is how 5G positioning works and Wi-Fi localization. When we go to high frequencies with large bandwidths and many antenna elements, this becomes a very interesting regime for localization. In 5G, we can do single anchor positioning using multipath information. We can do heading estimation, synchronization, environment mapping, all with a single base station. And we can operate a new kind of radar, maybe not at very high resolution for some applications, but still it can have some radar capabilities. And of course, this is now studied in 3GPP. Beyond 5G, we see great potential for intelligent services to boost localization performance and to enable localization. In contrast to communication, we typically like the line of sight path to be present when combined with a REIS, because it's really what provides us the diversity of geometrical information. Also, I think beyond 5G, as I mentioned before, communication and localization, they will go hand in hand. The communication can probably not work without the localization present. Nevertheless, there are many unanswered questions. There's an urgent need for measurements and hardware-compatible models, especially for beyond 5G, where hardware will be a main limitation. In general, I'm very happy to establish new collaboration. You are very welcome to contact me on this email address. I want to acknowledge several of the funding agencies that helped fund this research. And finally, I hope that in the next 10 years, when I show this picture, which shows two cars and this kind of red signal in between, and you ask me, is it radar or 6G or maybe 7G? I think the answer will be, it will be one and the same system. And with that, I thank you for your attention.
Thank you so much, Professor Henk Wemisch, for that very insightful presentation. And we're going to move straight to the question and answer segment. I believe we have a few questions from our audience, starting with this one. What do you see as the main challenges towards 6G localization and sensing? Prof, what do you think?
Without a doubt, it is the hardware limitations. Everything changes when we go beyond 100 gigahertz. We need to include effects of IQI imbalance, phase noise, amplifier nonlinearity, transmitter and receiver, mutual coupling effects. All of these effects will be much harder to deal with than for communication. In communication, you care about the end-to-end channel, right? The overall channel matrix is what you care about. For localization and sensing, you care about each of the geometric parameters inside of that channel. So this means you're affected by each of these hardware impairments severely. So we need ways to model these hardware impairments correctly and ways to mitigate them.
Thank you so much, and I hope that answered the question from our audience. Our second question that we have right over here is, are waveforms for localization and sensing different from those for communication? Are they?
That is yet unclear. I would say that any waveform for communication that has enough bandwidth and uses the angular resolution of the system well is suitable for localization and sensing. So my vision is that there will be a single waveform that will be parametric, for instance, like OFDM, where you can change the numerology, you can change the power allocation, and this flexibility will be used in one way for communication and another way for localization and sensing. But the underlying waveform will very likely be the same.
Thank you so much. We have a third question over here, and it is this. Will 6G localization offer something substantially new compared to 5G localization, or is it just better performance? What do you think?
I think in localization, the main difference will be better performance in terms of 3D positioning. So I do think it will be possible to go down to 10 centimeters or even lower. It will also allow more parameters of the state of devices to be measured. So not just the 3D position, but also the 3D orientation of devices, which is important for several applications. But in addition to localization, I think also the sensing aspect is important. 5G does not provide very good radar capabilities because the bandwidth is too small. But when you go to 6G, where you have multiple gigahertz of bandwidth, you become competitive with radar technologies, right? And I can imagine that a 6G radio unit can also serve as a radar for automotive applications. So these will be some of the main differences. And finally, because of the propagation effect at these very high frequencies, it is also possible that 6G waveforms can be used for spectroscopy or imaging applications that are not possible now. For instance, pollution monitoring or tissue imaging.
Thank you so much, Professor Wemisch, for that very inspiring presentation on localization in 5G and beyond, and for answering all those questions from our audience. That was truly a wonderful way to end our day. Thank you so much.
Thank you very much. Good evening.
Thank you so much.